So we assume that the reader at this point is already familiar with hyperreals. Okay, I was trying to figure out why the stream was not displaying the terminal window there. I figured out I had to reset something in the streaming software. Alright, now for this proof. If a ball is thrown in the air and its motion is governed by Newton's second law and the law by Newton's second law, with gravity being the only theorem. Assume a ball is thrown into the air and its motion is governed by Newton's second law. Assume the only force acting on the ball is the force of gravity. At time t equals 0. It's thrown in the air at time t thrown upward at time t equals 0. And its motion is governed by Newton's second law. Assume the only force acting on the ball is the force of gravity. Assume that for every real valued time t sub r, the height y of t sub r of the ball is real valued. Then for any finite non-real hyperreal time t sub h, the ball's trajectory is determined by y of t sub h. Okay, now we need to rule out before the ball was thrown up or after the ball hits the ground. So that big I equals the open interval from 0 to t sub final denote the interval to denote the time interval over which the ball has positive height. That t sub I and t sub f be the times when the ball is initially thrown and when it returns to its initial height, respectively. T sub I, T sub f, the initial and final times, be the times when the ball is initially thrown and when it returns to its initial height, respectively. Assume that for every real valued time t sub r in the closed interval from t sub I to t sub f, the height y of t sub r of the ball is real valued. Then for any finite hyperreal time t sub h with t sub I less t sub h less t sub f, the ball's trajectory is determined by y of t sub h. Proof. since t sub h is arbitrarily, since t sub h is, since the distance between t sub h and the standard part of t sub h is less than delta for all real delta bigger than 0, continuity of y implies that the standard part of I of t sub h so the idea is we know the height at time t sub h. We can take the standard part of t sub h to get a different time, which is close. Anyway, the height there, note that the distance between y of the standard part of t sub h minus y of t sub h is thus epsilon for all real epsilon bigger than 0. Thus, by assumption, since the standard part of t sub h is real, y of the standard part of t sub h is real. Since y of the standard part of t sub h is a real number, which is arbitrarily close to t sub h, it follows that y of the standard part of t sub h equals the standard part of y of t sub h. This should all be done in a lemma. Okay, now the definition of y prime of standard product t sub h. Well, we should say by definition. Well, let's see now. One use a line to start, so I'm going to need to include AMS math. Y prime of the standard product t sub h is equal to the limit as h goes to 0 of y of the standard product of t sub h minus plus, oh, h is already used for hyperreal, that confuses things. Let's say t goes to t sub h. Y of t minus t goes to standard product t sub h. Y of t minus y of t sub h divided by t minus t sub h. That's just definition of y prime. I claim that the standard part of t sub h minus y of standard product t sub h at the very beginning of the proof, let's let t equals, let's see, to reduce, to simplify notation, let t equals t sub h. Since the absolute value of t minus standard product t is less delta for all real delta bigger than 0, continuity of y implies that the absolute value of y of the standard product t minus y of t is less than epsilon for all real epsilon bigger than 0 by assumption. Since standard product t is real, y of the standard product t is real. Since y of the standard product t is a real number which is arbitrarily close to y of t, it follows that y of the standard product t equals the standard part of y of t. Again, that should be put in a lemma. Anyway, I claim that the standard part of the ratio y of t minus y of standard product t divided by t minus standard product t is equal to y prime of the standard part of t. To show this, it suffices to show that y of t minus y of standard part of t to show this, since y prime of standard part of t equals limit as h goes to 0 of equals limit as h goes to 0 of y of standard part of t plus h minus y of standard part of t over h it suffices to show that the fraction y of t minus y of standard part of t divided by t minus standard part of t can be rewritten as y of standard part of t plus h minus y of standard part of t all over h, where h equals t minus standard part of t. Since t is not in the reals, it follows that 0 is less than absolute product h less than delta for every positive real, for every real delta bigger than 0. Thus, by definition of y prime of standard part of t, the difference between y prime of standard part of t and this ratio The absolute value of the difference between y prime of standard part of t and the ratio of y of standard part of t plus h minus y of standard part of t all over h is less than epsilon for all real epsilon bigger than 0, which establishes the claim. Or I should say which says that the fraction in question i.e. the fraction in question is an infinitesimal distance from y prime of standard part of t, proving the claim. Thus, y of the standard part of t equals the standard part of y of t, and y prime of the standard part of t the claim shows that y prime of the standard part of t is determined by y of t equal is determined by y of t. Also, y of the standard part of t is determined by y of t, since y of the standard part of t equals the standard part of y of t. So y of t determines both the position and the velocity of the ball at time standard part of t. Clearly the standard part of t is in the interval between the closed interval from t initial to t final. And the position and velocity of the ball at some time, at any time within this interval, determine the ball's trajectory. That's a lot longer than I would like it to be, but good enough for now. Let's remark about how we stumbled upon this. Well, actually, the way we stumbled upon this is easier to explain once we've written down the motivation for hyperreals. Let's commit what we've done. Finished the rough draft of the proof. Okay, now let's go back to the section where we introduce the hyperreals. Now, rather than do this in the typical way, I'm going to do something equivalent, which is I'm going to do an electoral approach to the hyperrails, which is due to myself. And this isn't the first paper where it debuts, but it's equivalent to the standard introduction, but in my opinion, it's sort of more motivated. We give in this section, we will give an electoral construction of the hyperrails, which originally debuted in, fill in the citation later. This construction is equivalent to the standard One way to construct the hyperrails is to use ultrafilters. For the sake of self-containment, we will not assume prior familiarity with ultrafilters. Rather than we will introduce ultrafilters using an electoral approach, which originally debuted in da-da-da. Okay, so Do we want to take such a detour? It's not original, so we really shouldn't. The hyperreal numbers are star reals, the hyperreals, are an ordered field which extends the reals. The hyperreals include positive and negative infinite number. The hyperreals include infinite numbers, that is, there exists an R in star hyperreals include infinite numbers. We don't want to confuse the reader to think there's only a unique infinite number since there's many. There exists R in the hyperreals. A hyperreal number R is infinite is positive infinite the hyperreals include an isomorphic copy of the reals, but they also include infinite numbers, both positive and negative, and infinitesimal numbers, both positive and negative. The hyperreal numbers star reals are an ordered field extension of the reals first constructed by Robinson. We'll fill in the reference later. The following facts about the hyperreals are well known. Lemma. Well-known facts about the hyperreals. We'll enumerate these in a lemma so we can refer to them later, which makes things a little more formal, or a little more organized at least. There is, this has to go before the lemma. We'll say there is a canonical embedding of the reals in the hyperreals, and we identify each real with its corresponding. So we may identify each real with its corresponding hyperreal and act as if the reals are a subset of the hyperreals. The following facts about hyperreals are well known. The absolute value abs x of any hyperreal x is defined in the usual way as in any ordered field. The following facts about the hyperreals are well known. There exist infinite hyperreals, by which we mean x in the hyperreals such that absolute value of x is greater than r for every r in the reals. A hyperreal which is not infinite is called finite. There exist infinitesimal hyperreals, by which we mean x in the reals such that the absolute value of x is less than r for every real r bigger than 0. For every finite hyperreal x, there is a unique real number called the standard part of x, written standard part of x such that the distance between x and the standard part of x is less than epsilon for every real epsilon bigger than 0. Okay, now now for any function f on the reals, you have a corresponding star f. What's the best way to explain that without diving into the actual technical details, which we want to suppress as much as possible for the sake of making the paper simple, keeping the paper simple? Or do we even need to do that? Let's see. We could mention the transfer principle. We could mention the transfer principle. The transfer principle would apply to the differential equations governing the ball. And mention that in fact a very powerful and famous result is the transfer principle. which says that speaking formally, this principle says that every statement about every first order logical statement about the reals holds of every first order logical statement about the reals is true if and only if it is true about every first order logical statement about real numbers is true if and only if it is true about the hyperreals. For example, the statement there is no real x such that x squared equals -1 is true of the reals, and therefore, by the transfer principle, is true of the hyperreals. Another example, very relevant to us here, another example of the transfer principle, very relevant to us here. If it is true in the reals that a certain ODE has ODE's solutions that there exist solutions if it is true in the reals that a certain family of functions is exactly the set of solutions to a certain ODE, ordinary differential equation, then a certain family I sub r is one kind of f sub r are in the reals. Is exactly the set of solutions to a certain ODE, then the existence of said family implies the existence of a corresponding family star f sub r are in the hyperreals which is exactly the set of solutions of said ODE over the hyperreals. And each f sub r agrees with and HR in the reals star f sub r agrees with f sub r on the reals. In fact, it is possible to say much more. There is a mapping f maps to. There's a canonical mapping which takes every f rails to rails to a corresponding star f hyperrails to hyperrails extending f. Satisfy with no need to mention ODEs. However, for the details would complicate this paper, but the details would further complicate this paper. In our case, we care about the ODE governing the motion of a ball subject to Newton's second law and gravity. A ball thrown upward from initial at 0 at time 0, subject to Newton's law and gravity. Newton's second law and gravity. Make this a new paragraph. In our case, we care about the ODE governing the motion of a ball thrown upward from initial height 0 at time 0, subject to Newton's second law and gravity. The family F sub r are in the reals. Of solutions to this ODE is indexed by the initial velocity r of the ball. By the previous paragraph, there's a family star F sub r are in the hyperreals. The solutions to set ODE over the hyperreals can be written as star F sub r are in the hyperreals where each star where every r in the reals star F sub r extends F sub r. We may identify each F sub r, therefore, with star F sub r without risk of confusion. This is just a very formal technical way of justifying talking about the ball's height at non-real hyperreal times. The above is just a very formal technical way of justifying talking about the ball's height at non-real hyperreal times. Not only does the ball have heights at non-real hyperreal times, those heights obey the exact same ODE which governs the ball's heights at real times. Thus, we extend the motion of the ball into hyperreal times in such a way as to respect the laws of physics. We are not arbitrarily filling in the gaps. Newton's second law fills them in for us in a physically realistic way. Great. Do we need any other preliminaries about the hyperreals? Not sure if we do. Let's compile this. Oh, right. Need to define standard part. And we're going to need to declare some theorems. Undefined control sequence on line 43. We need AMS sim in order to use the reals. And all these M boxes should probably be math RMs. Okay, now why is it we should have the abstract after the make title. Great. You notice you always write the abstract dead last, because of course, before you write the paper, you don't actually know what's going to be in the paper. Okay, let's do a quick proofread of the whole thing so far. Trajectory determined by snapshot at a finite hyperreal time. Introduction. Suppose someone throws a ball in the air and takes a photograph of it in the air. They give you the photograph, which has a timestamp attached to it, so you know the height of the ball at a given time t snap. Assuming that the ball's motion is governed by Newton's second law of motion, force equals ma, and that gravity is the lone force acting on the ball, can you deduce the ball's entire trajectory? In almost all cases, the answer is an emphatic no. But perhaps there is an exception. Assume that the physics of our universe are such that at every real valued time, the height of this ball is real valued. And assume that the differential equations governing the ball's height are valid not only at real times t, but also at times t plus epsilon whenever epsilon is a positive or negative infinitesimal. We will make this more formal below. This assumption is a mild assumption because of the so-called transfer principle from non-standard analysis, which we will also discuss below. Believe it or not, from the above assumptions, it follows that if our timestamp t snap happens to be a finite non-real hyperreal, in other words, if t snap equals t real plus epsilon for some real t real and some positive or negative infinitesimal epsilon, then in fact the snapshot does determine the entire trajectory of the ball. The proof is surprisingly very simple. Let's delete that whole paragraph. I mean that whole blurb. A polynomial precedent. The claim we made in the introduction might seem more believable if the reader considers the following. Suppose a particle is moving in one dimension and has position p of t at every real time t, where p in rationals adjoint x is a polynomial with rational coefficients. Knowledge of the particle's position at, say, time t equals 0 or t equals 1, or even at time t equals 1/2, clearly does not determine the particle's entire trajectory. For example, if p of 1 equals 5, then the particle's trajectory could be p of t equals 5, non-stationary. Non-stationary, that should be stationary. For example, if p of 1 equals 5, then the particle's trajectory could be p of t equals 5, stationary, or p of t equals t plus 4, or p of t equals 1/2 t squared plus 9/2. Let's check that real quick. Yeah. Or any number of other candidates. However, for any transcendental number alpha, the particle's position at time t equals alpha in fact does determine the particle's trajectory. For if p1, p2 in rationals adjoint x were two distinct candidates, both of which would put the particle at set position at time alpha, then this would imply p1 of alpha equals p2 of alpha, thus p1 minus p2 quantity of alpha equals 0, contradicting the transcendentality of alpha. If we assume that the physics in our universe are such that particles have algebraic positions at algebraic times, then it follows by elementary ballistics that the ball from the introduction has position given by a polynomial in rationals adjoint x. Thus the ball's entire trajectory is determined if the snapshot is given at a transcendental time t snap. We could end the whole paper right here with no need to talk about infinitesimals if we were willing to assume that particles have algebraic positions at algebraic times. But perhaps that assumption is unrealistic. It does not seem physically unreasonable to talk about ballistics of balls with, say, initial height pi equals 3.1415 ... Let's shorten that to just 3.14 ... Everybody knows what we're talking about. However, it does seem physically plausible to assume more weakly that particles in our universe occupy real-valued positions at real-valued times. And under that assumption, we will arrive at the seeming paradox from the introduction. The hyperreals. The hyperreal numbers are an ordered field extension of the reals, first constructed by Robinson. I'll fill in that reference later. There is a canonical embedding of the reals in the hyperreals, so we may identify each real with its corresponding hyperreal and act as if the reals are a subset of the hyperreals. The absolute value, abs x, of any hyperreal x is defined in the usual way as in any ordered field. The following facts about the hyperreals are well known. Lemma, well-known facts about the hyperreals. 1. There exist infinite hyperreals, by which we mean x in the hyperreals such that abs x bigger than r for every r in the reals. A hyperreal which is not infinite is called finite. 2. There exist infinitesimal hyperreals, by which we mean x in the hyperreals such that abs x less than r for every real r bigger than 0. 3. For every finite hyperreal x, there is a unique real number called the standard part of x, certain standard part of x, such that abs x minus standard part of x less epsilon for every real epsilon bigger than 0. A very powerful and famous result is the transfer principle. Speaking informally, this principle says that every first-order logical statement about real numbers is true if and only if it is true about the hyperreals. For example, the statement, there is no real x such that x squared equals minus 1, is true of the reals, and therefore by the transfer principle is also true of the hyperreals. Another example of the transfer principle, very relevant to us here. If it is true in the reals that a certain family Fr are in the reals is exactly the set of solutions to a certain ODE, then the existence of said family implies the existence of a corresponding family star Fr are in the hyperreals, which is exactly the set of solutions of said ODE over the hyperreals, and for each r in the reals, star Fr agrees with Fr on the reals. In fact, it is possible to say much more. There is a canonical mapping which takes every f reals to a corresponding star f hyperreals to hyperreals extending f with no need to mention ODEs, but the details would further complicate this paper. In our case, we care about the ODE governing the motion of a ball thrown upward from initial height 0 at time 0, subject to Newton's second law of gravity. The family Fr are in the reals of solutions to this ODE is indexed by the initial velocity r of the ball. By the previous paragraph, the solutions to said ODE over the hyperreals can be written as star Fr are in the hyperreals, where for every r in the reals, star Fr extends Fr. We may identify each Fr, therefore, with star Fr without risk of confusion. The above is just a very formal technical way of justifying talking about the ball's height at non-real hyperreal times. Not only does the ball have heights at non-real hyperreal times, those heights obey the exact same ODE which governs the ball's heights at real times. Thus, we extend the motion of the ball into hyperreal times in such a way as to respect the laws of physics. We are not arbitrarily filling in the gaps. Newton's second law fills them in for us in a physically realistic way. The proof. Theorem. Assume a ball is thrown upward at time t equals 0 and its motion is governed by Newton's second law. Assume the only force acting on the ball is the force of gravity. Let ti, fi, the initial and final times, be the times when the ball is initially thrown and when it returns to its initial height, respectively. We need to rewrite this because we want the family to be indexed by single reals, so we want to make sure that the ball is thrown initially from height 0. I'll do that tomorrow. It's annoying because the theorem would work even without that condition, but then that would complicate the previous section. Assume that for every real valued time tr in the closed interval from ti to tf, the height y of tr of the ball is real valued. Then for any finite non-real hyperreal time th with ti less th less tf, the ball's trajectory is determined by y of th. Proof. To simplify notation, let t equals th. Since abs t minus standard part of t is less delta for all real delta bigger than 0, continuity of y implies that abs y of standard part of t minus y of t is less than epsilon for all real epsilon bigger than 0. It reads nicer if we switch the order of the first abs value. Since abs standard part of t minus t is less than delta. Since abs standard part of t minus p is less delta for all real delta bigger than 0, continuity of y implies that abs y of the standard part of t minus y of t is less than epsilon for all real epsilon bigger than 0. By assumption, since the standard part of t is in the reals, y of the standard part of t is in the reals. Since y of the standard part of t is a real number which is arbitrarily close to y of t, it follows that y of standard part of t equals the standard part of y of t. I claim that the standard part of the fraction y of t minus y of standard part of t quantity over t minus standard part of t equals y prime of the standard part of t. The fraction y of t minus y of standard part of t quantity over t minus the standard part of t can be rewritten as, let's break that up. Make that an inline proper fraction. The fraction y of t minus y of standard part of t quantity over t minus standard part of t can be rewritten as y of standard part of t plus h minus y of standard part of t quantity over h, where h equals t minus the standard part of t. Since t is not in the reals, did we? Yes, we explicitly said th is a non-real hyperreal. Since t is not in the reals, it follows that 0 is less than abs h less delta for every real delta bigger than 0. Thus, by definition of y prime of standard part of t, the absolute value of y prime of standard part of t minus y of the standard part of t plus h minus y of standard part of t quantity over h is less than epsilon for all real epsilon bigger than 0, i.e. the fraction in question is an infinitesimal distance from y prime of standard part of t, proving the claim. Well, that doesn't immediately prove the claim. We need to use the fact that it is real. But the fraction in question is... yeah. Well, the fraction in question isn't real, but its standard part is real. The claim follows. Maybe tomorrow I'll think about whether there's a better way to spell that out. I don't know if we need to go into that much detail. Anyway, the claim shows that y prime of standard part of t is determined by y of t. Also, y of standard part of t is determined by y of t, since y of standard part of t equals standard part of y of t. So y of t determines both the position and the velocity of the ball at time standard part of t. Clearly, standard part of t is in the closed interval from t initial to t final. Maybe I should say something more about that. And the position and velocity of the ball at any time within this interval determine the ball's trajectory. Let's commit the proofreading. All right. Let's wrap up there for now. I'm Samuel Allen Alexander. Please like, comment, and subscribe, and I'll see you in the next video.